Good. Today, we will start with a second part of this chapter, which is called as electromagnetic induction. Now, what exactly is induction? We will talk about this, right? Just give me a second. All right, it's here. Now, few points. We have seen the motor, we have seen how the electricity produces a magnet here, right? Now, question arises, and that question actually comes in different scientists' mind, that is it really possible that if electricity produces a magnetism, is it really possible that magnetism produces an electricity? Now, this thinking is unique thinking. And on that thinking, there are two different scientists who actually worked. One scientist is Faraday, and the other scientist is the Lenz. And they gave their laws about it, and they used to work for that. And while they used to work for that, they actually worked too much on that. So, electromagnetic induction is a study of sciences in which we study how the electricity produces, how the magnetism is producing the electricity. What will happen when the magnetism produces an electricity? Okay. So, major work is being done by Faraday. Now, this way, you can check it out. This magnetism produces the voltage, or you can say induced voltage. Now, how does it happen? The first thing that actually comes in the mind is, how does it happen that a magnetism produces a current, right? So, for that, there are a few things which are very, very important. If you check this one out, what we have noticed that if you just increase the wire, if you move the wire faster within the magnet, current produces, right? If you have strong magnets, current produces. If you increase the length of a wire in a magnetic field, or you can say multiple loops in here, you can say current increases, right? Now let's talk about few things, which is very, very important in this. So Faraday is saying that the induced EMF, is basically of a conductor is proportional to the rate at which the magnetic field lines are cutting by the conductor. Now, what exactly it is? Let's talk about this. Now, this is very interesting diagram. We will come back to that Faraday law then. We have done one thing. We have took a simple coil like that, which is there right in front of you. And that coil is connected with a ammeter, right? Now, what we have done, we have taken a bar magnet, any pole, North Pole or South Pole, whatever, and we placed near to the coil. Now, what we have noticed, no current is produced, right? Because that needle stay where it is. Importantly, once you start moving that bar within the coil, needle shows movement. That's strange, right? Because while you are moving the magnet towards or inside the coil, the needle shows the deflection. And when you're moving the coil, when you're moving the magnet out of the coil, needle again shows the deflection, but in the opposite direction. Needle shows the direction means current is there. So what exactly is the scene? If a bar magnet is pushed into the coil of a wire, an EMF is induced in a coil. If a magnet is withdrawn from the coil, then EMF is induced in the opposite direction. That's why these needles are showing the to opposite direction of the movement of the coil or coil, current directions. So technically speaking, when the magnet is placed simply away from the coil, we know that magnetic field lines are coming out of it. They are also associating with the coil as well. They are cutting the coil as well, but they do not produce any induced current or a voltage. But as soon as you start moving the coil into the coil, now what exactly is happening? The rate of change of magnetic lines cutting the conductor or cutting the coil, that changes. And when that rate of change of magnetic line cutting the coil changes, that actually produces a voltage or an induced voltage within the coil. So basically, now you understand, we have to go back a bit. EMF induced in a conductor is proportional to the rate at which the magnetic field lines are cutting the conductor. How can you increase that? Moving the wire fastly, speed definitely, using a strong magnet, or you more thing, number of coils will be more. This law is basically called as Faraday law, right? So Faraday is saying like this. So induced EMF can be increased by moving the magnet faster, using the stronger magnet, or increasing the turns of the coil. Now, one more thing which is very, very important. This is what we called as Faraday law or Faraday law, whatever. Now, once you understand the Faraday law, at this point, we didn't talk about any pole or anything. Now, for example, you got the same coil, same voltage source or a current source. Now, I'm specifically mentioning that suppose the North Pole is going here and South Pole is here. Now, what Lenz is talking about is that once the magnet comes closer or moves towards the coil, the EMF induced in the coil, right? And that EMF always try to oppose the reason of producing it. Now, what does it mean is, now because EMF is induced due to you move the north pole of a magnet towards the coil. So EMF is produced because you are moving it towards the coil, right? Now, once you're moving it towards the coil, EMF is induced, done, sorted. But the problem is started that EMF which is produced inside the coil that tries to oppose the reason of producing it. And what is the reason? You're bringing that coil towards the, you're bringing that magnet towards the coil. So how do it actually opposes it? Because we know that once the induced EMF is produced, the current is also, going through the coil. Now, how do it oppose the movement of magnet towards it? This side becomes a north pole, and the opposite side, which is not facing the magnet, is a south pole. So north-north will repel each other. So you have to work against that. That is what it does. And when you're moving the magnet away, now what happened? Again, EMF is induced and tries to oppose the reason of producing it. So in that case, when you are going against it, you are going away from the coil, that side become a south pole, and the side which is not facing become a north pole. In that phase, that tries to attract towards itself. So by making itself as a north pole and a south pole, it tries to oppose the reason of producing it. That is what the Lenz law is saying. So what is Lenz law? Lenz law is saying when the magnet is moving towards or away from the coil, right? The induced EMF produced in the coil which is always try to oppose the reason of producing it. That is what we called as Lenz law. So in that case, we will find out that how the magnetism will be. So if that is the reason, you can see yourself the direction of the voltage which is produced here will always opposes. So the AC voltage is generated. That's why the generator is always a AC generator. All right. Okay. Now, once you understand that, now remember one more thing. Let's come to that. Now, this is DC. DC shows a straight line, which means that it won't vary with the time. And it just shows a straight line, which means it has a constant voltage or a constant current, right? Next, AC. If you check it out, AC is continuously changing its value as well as direction is changing. It has frequency and everything. In the United Kingdom, you can see yourself 230 volts, and the frequency we have it is 50 hertz, right? Now, one of the on that principle electromagnetic induction, we have a device named generator, AC generator. Now, what does it do? It converts the mechanical energy into electrical energy. Shape is almost the same as the motor, but there is a small difference. Here you can see yourself. These are the and this one needs to be rotated as we do it with our hands, right? All the things are same. You can see yourself. So two things are required: permanent magnet and a moving wire. So here carbon brushes are the same. They are just giving you the connection between. So slip ring are fixed to the coil and rotate within. Okay. So coil made of insulation wire rotating in the magnet field by turning the shaft. So you just do it mechanically, and while doing mechanically, the electricity will be produced within that. We also called it alternator. Previously, we have seen split ring. Here it's a slip ring. Slip ring brushes, they are just connection to the armature body and all that. So here you rotate the coil with the hands, right? And why do you do that? AC supply is generated here, which will be taken as electric energy. So that's how the that's how the mechanics, and mechanical energy converts into electric energy. So what will be the procedure? What will happen when it's a Faraday law? When you can simply think of it, when you produce a rate of change of magnetic flux, or you can say the magnetic line cutting the conductor, you do it, it produces an electric current or induced voltage, and that is what we called as uh, electromagnetic induction. And that is the procedure to actually getting the electric energy from the mechanical energy. Now, split ring have are fixed for the coil and rotate within. Brushes normally carbon brush rub against the slip ring, right? Now, there are two, three things. Slip ring details. Brushes keep the coil connecting to the outside part of a circuit. As coil rotate, it cuts the magnetic field line, so an EMF is generated, as I just said it. Slip ring keep the coil in contact with the brushes throughout the rotation, and as result, the current flows in alternate direction. Okay, so and as a result, the current flows in alternate directions, producing an alternating. Keep changing it, and so current produces. That is a waveform of it. You can see the current values changes as the time progresses. Now, if you check this one out, the one going above, it means that coil is rotating in the forward direction. Then here, the direction is going to change. Here, maximum reverse current. direction is going to change. So if maximum EMF can be increased by increasing the number of turns, increasing the area of a coil, and using a strong magnet. Now, this is interesting again. This one is when it rotates forward, right? And this one is the maximum reverse current, right? Now, one more apparatus which is also using the same phenomena as we called it transformers. They are used to increase or decrease the voltage. Now remember that they are used to step up or step down the voltages. But remember that it won't work on DCs. They work on ACs because there is a reason for that. Now check it out. This is one of the transformer shape. You can see this is an iron core. There is an input coil. There is an output coil. Input coil is called as primary coil. Output coil is called as secondary. Now you give AC input voltage. Why AC? Because you are providing it a current, first of all. And secondly, it's a continuously changing current. Because rather you move the coil or you move, magnet is fixed, even coil is fixed. So what are changing? What are you changing? You are changing the current. This current value once passes through the coil, it produces a magnetic field. But that magnetic field is not the fixed magnetic field, but changing magnetic field. That changing magnetic field, or you can say rate of change of magnetic flux, cutting the conductor on the secondary side produces, and that produces your output voltage. Now, this is very interesting. If you check it out, on the input side, the number of turns are less. At output side, the number of turns are more. So we call this a step up transform. If the output number of coils are more than the input number of coils, we called it a step up transformer. We called it a step down transformer. So technically, in this case, we can increase the output voltage from the input voltage, right? So in a step down transformer, the voltage will be decreased. Now, when AC flows through the primary coil, it set up an alternating magnetic field in the soft iron core, and therefore in secondary coil, this changing field induced an alternate voltage in the secondary, right? Now there is a formula there. Please check it out. Voltage is directly proportional to the number of turns. V2 upon V1 is equal to N2 upon N1. N2 means number of secondary, N1 means number of primary, V2 is voltage at secondary, and V1 is voltage at primary, right? Now check this out. This is the formula we have it. Example, our transformer has 20 turns on the primary and 10 turns on the secondary. Now this is step down transformer because the number of turns at secondary is less. If the input voltage is 50, what is the output voltage? Check it out, it is less. Same formula, V2 upon V1 is equal to N2 upon N1. You just manipulate it and you found out it's 25. Right? Now, these are the values. Primary, secondary voltages are given even number of N1 is given, and they are asking you N2 or asking you it's a step up or step down. First of all, it's 12 to 24, so it's a step up transformer. 400 to 200 step down. 25,000 to 50,000 step up. 23 to 230 is step up, right? Now, rest you just need to find out by using a formula V2 upon V1 is equal to N2 upon N. And you can simply find out the values to it. Okay. I hope you understand the topic. Our chapter is finished. And inshallah, in the next chapter, hopefully, we will do the last chapter, which is our space physics. That will be our 32nd chapter. So hope to see you in 32nd lesson. And bye from my side.